Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the topic which we discussed in the last two lectures. So let me write the topic. Our topic was application of statistical method to gases. So we are continuing that in today's lecture as well. So let me underline it. So it is continued. Let me refresh your memory. In the last two lectures, we outlined or discussed the difference between the application of statistical method to distinguishable localized particles and the application of the same method to the gases. We discussed the issue of large number of states available in case of gases. We talked about the indistinguishability of gas particles. Then we talked about how we resolve these things using the quantum ideas. We talked about the density of states function in K, then energy, dispersion relation. We talked about that density of states function with regard to its form in 3 dimensions, 2 dimensions, and 1 dimension. Then we discussed how we group the states in case of gases, because the states number of states is very large, and we talked about how to incorporate in the density of states function or number of states which we count in certain k interval, how we incorporate in that the spin factor g, and lastly we defined the filling factor Fi as the, which is also called distribution function, as the average number of particles per state. So let us continue. Now next thing, in the application of statistical method to gases is to count the number of microstates corresponding to a particular distribution. Let us discuss that idea. So next step is to count the number of microstates corresponding to a particular distribution. To a particular distribution. A microstate relates to a quantum state of all n particles in the gas. So we need to recognize that identical gas particles are fundamentally indistinguishable from each other. They are, they are therefore effectively competing for the same one particle states. I repeat, identical gas particles are fundamentally indistinguishable from each other. They are therefore effectively competing for the same one particle states. Therefore, we can never define which particle is in a particular state. Let me underline this. Let me write it a different color. We can never define, we can never define which particle is in a particular state, is in a particular state. That is not possible because identical gas particles are indistinguishable. Then what we do, how we specify the microstate completely in this case. What we do, we specify the microstate completely by merely stating how many particles are in each state. This is important. We specify the microstate by stating how many particles are in each state. Right? Now, in this regard, there is another important question to be addressed when we have to specify this thing, that how many particles are in each state. What is that important question? That is, in quantum mechanics, there are two different types of identical particles which obey different rules as to how many particles can be allowed in each state. The particle types are called fermions and bosons. Right? So we have in quantum mechanics two different varieties of identical particles with regard to the rules they obey to how many particles can be allowed in each state. The particles are called fermions and bosons. To make this clear, consider a system of just two identical indistinguishable particles. So consider a system of just two identical indistinguishable particles, right? Now, this system is described in quantum mechanics by a two-particle wave function psi of 1 comma 2, while the label 1 is used to represent all the coordinates. By all the coordinates, I mean space and spin coordinates of particle 1. And label 2 represents all the coordinates pertaining to particle 2. Now, for this wave function psi 1 of 2, 1 comma 2, to be a valid wave function, two conditions must be satisfied. So to be valid, two conditions must be satisfied. One is obviously that it should be a valid solution of Schrodinger's equation, and the second condition is that it should satisfy the correct symmetry requirement for interchange of the two labels. I repeat, the second condition is that it should satisfy the correct symmetry requirement for interchange of the two labels. Right? What does that mean? That means if the labels of the two particles are interchangeable, that means you label particle 2 as particle 1 and particle 1 as particle 2. That means you change the labels. Then any physical observable cannot change since the particles are identical. Let me write it. So two conditions must be satisfied by this wave function. One, it must be the solution of the valid solution of Schrodinger's equation. Second, it must satisfy the correct symmetry requirement for interchange of the two labels. What does that mean? That means if the labels of the two particles are interchanged, are interchanged, then any physical observable pertaining to the system is understood. Then let me adjust my pen. Any physical observable cannot change. Why? Because the particles are identical. Now, how we write this thing mathematically? That means psi 1 of 2 must be equal to exponential of iota delta psi of 2 1. Understand it, don't get confused. What is the difference between Psi12 and Psi21? In Psi21, you have interchanged the label. You have labeled now particle 1 as 2 and particle 2 as 1. Now physical observables must not change because the particles are uh, identical. By interchanging their labels, no physical observable will get affected. That means mathematically this. Why so? Since physical observables always involve the product psi star psi. Those physical observables are not directly involved with psi, they are involved with the product psi star psi, where psi star is the complex conjugate of psi, and this iota in this exponential is the square root of -1. See, the wave functions are related by the phase factor exponential of iota delta. But if we make two interchanges, then we come to the mathematical identity. That means if we interchange the labels twice, first we get psi12 is exponential of iota delta times psi of 2 1. Then you make again interchange. Then here you will get exponential twice iota delta, because you have to write exponential iota delta times exponential iota delta times psi12. So when you interchange the labels twice, you get back your psi12 wave function. So psi12 must be equal exponential of twice iota delta psi12. That in other words means that exponential of twice iota delta is equal to 1. And therefore the interchange factor, which is exponential of iota delta, must equal +1 or -1. One of the two square roots of +1. Right? Now particles which interchange coordinates with the +1 factor are called bosons. So this variety of particles is bosons. And the particles for which this which interchange coordinates with the -1 factor are fermions. They are fermions. Right? So what we do, we say that bosons are uh, described by the symmetric wave function. That means psi12 is plus time 1 times psi21. If you interchange the label of the particles, there is nothing is going to happen to the wave function. It is symmetric under this operation. But For fermions, psi1 2 will be equal to minus 1 times psi2 1. So we say their wave function is antisymmetric. So bosons have symmetric wave function and fermions have antisymmetric wave function, right? Now, it can be taken as an experimental result that all particles, all particles with integral spin, that is 0, 1, 2, comma, so on, are bosons, right? Whereas those particles which have odd half integral spins. My pen, let me adjust my pen. So those particles with odd half integral spin, that is half, 3 by 2, then 5 by 2, and so on, they are fermions. Therefore, electrons, helium-3 atoms have spin half their fermions. Photons have spin 1, helium-4 particles have spin 0, they are bosons. Next thing is, when we consider the case where the particles are weakly interacting, let me consider the next point. Next point. Next point is, we are talking about the weakly interacting particles. Weakly interacting particles. For weakly interacting particles, which is the relevant case for our statistical physics, the solution to a Schrodinger equation for two particles can be written as the product of two one-particle wave functions. That means this. My wave function for the combined two particle system, particle 1 and particle 2, can be written as the product of two one-particle wave functions. That means psi 1 of A, psi 2. Let me write it equation first. What is here A and B? One is referring to the particle. What about A and B? These labels A and B are two values of the state label, which we have in the last lectures denoted by the letter J. So A and B are the two values of the state label J for the one particle states, right? But there is more to it. The wave function given by equation 1, it's okay that it considers the weakly interacting situation, but it has an issue. It suffers the defect that it has no interchange parity. Let me write it. It has no interchange parity. It has no interchange parity. That, in other words, means it is neither, let me write it with different color. It is neither a symmetric wave function, I denote by S, nor antisymmetric wave function, which I denote by A. That means in this, if you uh, interchange the label of the particle 1 and particle 2, you will not get psi 1, neither you will not get psi 1 2 is plus times psi 1 2, psi 2 1, nor you will get psi 1 2 is minus times psi 2 1. You can check it. You can take it as a home assignment. So check it. So therefore, this cannot represent the wave function for two particle system when we are considering these fermions or uh, bosons. That means these particles, because for bosons are represented by symmetric wave functions and fermions by antisymmetric wave functions. Then what we do, we combine the interchanged partner of equation 1 with equation 1 to get the required symmetric and antisymmetric wave function. That is, we do get this. Symmetric wave function psi s 1 comma 2 is 1 over square root of 2 times psi a of 1 psi b of 2 plus psi a of 2 psi b of, let me clear it, psi b of 1. This is, let me make the same bracket here. Let me name it equation 3, or equation 2. This is my equation 2. And the antisymmetric wave function required for the fermion case, psi a of 1 2 is equal to 1 by square root of 2 psi a of 1 psi b of 2 minus psi a of 2 psi b of 1. This is my equation 3rd. Let me check it. Psi s 1 comma 2 1 by square root of 2 psi a of 1 psi b of 2 plus psi a of 2 psi b of 1. Then I have psi a 1 comma 2 is 1 by square root of 2 psi a of 1 psi b of 2 minus psi a of 2 psi b of 1. This is how we construct the required wave functions, symmetric wave function for bosons and antisymmetric wave function for fermions for the two-particle system. You can check it that these functions given by equation 2 and 3 possess the correct parity, namely, if you check it, psi S12 is equal to plus psi S21, and for antisymmetric wave function psi A12 is equal to minus psi A21. Check this, right? 1 by square root of 2 factors are for normalization purposes. Now, equations 2 and 3 bring out a fundamental difference between bosons and fermions, which I need to highlight here. Consider the situation in which the labels A and B are identical. If A is equal to B, that means the two particles both are competing for the same particle state, same state. Now, for bosons for which equation 2 applies, there is no problem, because in equation 2, if you make A is equal to B, the wave function will be enhanced wave function compared to previous situation. But on the other hand, fermions are quite different. The wave function given by equation 3 vanishes identically when you set A equal to B. If you make A equal to B in equation 3, you can see psi A of 1 of 2 will become 0 if you make A equal to B. This will vanish. So fermions are different. What is the meaning of that? The meaning of that is no two identical fermions can occupy the same state. Let me write it. No two identical fermions can occupy the same state, the same state. So this is the rule. No two identical fermions can occupy the same state, because as I told you, when you make A equal to B, the wave function vanishes. Now this has a name. This statement has a name. It is called Pauli's exclusion principle. The fermions obey the Pauli's exclusion principle, right? Bosons have no such restriction. We say bosons are friendly particles and fermions are unfriendly. So bosons enjoy multiple occupancy of states, but in the fermion case, all the states are either unoccupied or singly occupied. Finally, We may readily generalize all the above results to an assembly containing n rather than merely two identical particles. The interchange argument is still valid between any pair of particles. For our assembly of n weakly interacting particles, the generalizations of these equations 1, 2, and 3 are obvious. This equation 1 uh, becomes an extended product of n1 particle terms. For bosons, the expression for sigma s, psi s, that is equation 2, would be similar to equation 2 for n particles, except that it contains their n factorial terms, because every permutation of the particle coordinate labels are combined, are to be considered, and all terms will have a positive sign, and there the normalization factor will be 1 by square root of n factorial, not 1 by square root of 2. Similarly, for fermions, the generalization of equation 3, because they have antisymmetric wave function, is will contain again the n factorial terms, but they will have systematically alternating signs, one positive then negative, and normalization factor will be 1 by square root of n factorial. So this is here I stop. This all for today. We will continue. We are discussing how to apply the statistical method to gases. So before stopping, I will give a small summary. Now we know that first thing is how we count the microstates in case of gases corresponding to a particular distribution. I told you that we can never define uh, which particle is in a particular state, because particles are indistinguishable. Then how we specify microstate? We specified by stating how many particles are in each state. Now, with regard to this question, we have two varieties of identical particles, fermions and bosons. Fermions have antisymmetric wave function, and bosons have symmetric wave function. Then we talked about how we write their wave functions when they are weakly interacting, and we discuss these equations 2 and 3. Then we talked about the Pauli exclusion principle, that for fermions there is a restriction that no two identical fermions can occupy the same state. So in fermions, either all the states are singly occupied or unoccupied. Bosons have not this restriction. We say they are friendly particles. They enjoy multiple occupancy of states. So this is all for today. Thank you. Don't forget to like, share, and subscribe my channel. Assalamu alaikum.